Okay, hello everyone. We're going to move into the section 2 in unit 1. So we are still in chapter 18 in your textbook. But in this section, actually, we are planning to discuss about the electric field and electric field line and also electric dipole and finally about the capacitor. So now, so far what we know is we discussed about the electric force that by using Coulomb's law, if you have two charged particles, these two charged particles can have attraction if they are opposite charges. If they are same sign charges, they're going to repel each other. So this attraction and repulsion will be able to calculate by using Coulomb's law that we discussed, and that is the magnitude, direction of the forces. We need to draw the free body diagram and we need to find it out which direction your force acting on that particle. So now that is the electric force. Now, after we learn the electric force, we can discuss about the electric field. So now electric field is defined it as electric force per unit charge. So when I say per unit charge means if I have a charge particle in here, that charge particle will create an electric field around this charge particle. So what that means is when I bring another small test charge, this charge going to be known that this charge is exist in the environment. That feeling, this charge field is called it as the electric field. That's why electric field on charge particle is depend on force per unit charge. That means force divided by this simple charge. We call it as the electric field. That's why electric field does not have the charge of this particle. You're going to get the force per unit charge. That means it is independent of the test charge that you're going to bring to the environment. So now that's the part that we're going to discuss in today's class. So now let's share the screen first. Okay, so now we are still in chapter 18 in your textbook and part 2, and your lecture will be this one. And full screen. So we're going to talk about electric field in this section, and Gauss law is the relation to electric field, and how we calculate the electric field is coming from the Gauss law. And then we're going to discuss a little bit about the conductors and electrostatic applications. Okay, so now content of this chapter, again, about electric field. That's the most important part we're going to discuss. And then we're going to discuss about a little bit about the electric dipole and the capacitor at the end, and then some applications. So now electric field, as I mentioned, if I have a charged particle, this Q1 is already on the environment, that charged particle will be there. But when you bring the test charge Q2, that charge knows there is another charge. That feeling the second charge, we call it as the electric field. So now this will be basically how we're going to examine the system. That charge particle that your test charge field above the other charge particle is called it as the electric field. That means this particle itself will create the electric field. Now when I bring the second particle, this particle knows what is the first particle is, then that feeling we call it as the electric field. That means this will be your source charge, and this is the test charge you bring. So now when I bring the test charge, this particle feels something in this direction. That something we call it as the electric field, and we're going to use the symbol uppercase E to show the that field. So now Now let's think about the how this electric field will work. So now electric field, as a definition, it is a force per unit charge. Force measured by newtons and charge measured by coulombs. Newtons per coulomb is the unit of electric field. So now what is that lowercase q is? Lowercase q here is actually, this q is the test charge. Charge. Okay, so what that means is, if I have a charge in here, negative charge, a big charge, that will be the source charge, right? So this is the test charge that I will bring. Now we know that negative and positive will attract each other. Because of that, there is a force on the test charge. That is the force that I have it in here as the force, right? So that force, if you take that force and divide by this charge, that is, we call it as the electric field. So now if it is a positive charge sitting closer to the negative charge, that electric field direction will be the force direction, right? Because this particle will feel that it is going to attract into the negative charge. That is the feeling. That will be the same direction as the force direction in this case. Electric field and force for the positive charge will be the same direction. But if you have a negative charge, then you're going to see the direction is opposite direction. Okay, so that we're going to discuss in later, but electric field is force per unit charge. For the positive charge, direction is same direction as force. For the negative charge, because you're going to get the negative in here, because of that you have the negative direction of the electric field. But let's get an understanding how to get the formula for that. Now, force per unit charge. Force in Coulomb's law, we know that K, Q, Q, two charges, Q and lower Q, if this one is Q, right? You can use any notation. Here I'm using Q and Q. In my last session, I used the Q1 and Q2 because I want you to familiarize with the different notations. It's just a notation to show that you have two charges, right? So Q and Q divide by R square. This is the Coulomb force, as we know, between these two charges. If you divide that by the source charge, then the test charge, then you're going to cancel out the test charge. That means at the end, you're going to stay your electric field only depend on the source charge. Uppercase Q here is the source charge. Again, these all are magnitude. I don't have any direction on this equation yet. Direction is coming from the your positive and negative information or the free body diagram you need to draw. That will give you the direction of electric field. Okay, so now how to understand this one by compare to your physics 1 class. So we know that if I have an object, this object has the force of gravity straight downward. If I try to push that object up, I need to do some work, right? Similar to that, when I have a charge particle, this charge particle has a QE electric force, then this electric force is the one that you apply to lift the particle, right? So it will be same work that you have to do in gravitational lifting up or the electric force lifting up. Is still there is a force and distance that travel. Because of that, there is a work done for both cases. It's like similar situation, right? So now this all electric field, electric force, everything is vectors. Is still we are using superposition principle after you draw the free body diagram to solve the problems. Okay, it's very important. So now more into the electric field. So if you have a positive charge, I told you that electric field will be same direction as your electric force. You know that this is positive, this is positive. This will create the electric force this way because they are repelling each other. Electric field also have the same direction, but it is only depend on the source charge Q over K times Q over R square. This distance is R, and F is K times Q naught in this case, divided by R square. That's the difference between force and the electric field. If it is a negative charge, you know that negative charge has the electric force direction this way, but it's still your electric field direction same way. We'll say I have negative charge here. So now if it is a negative charge, this is Q naught, now it is negative, right? Now what happen is positive and negative will attract each other. That means my electric force is this way. We know that because attraction, but what way the electric field is? Electric field will be this particle created by the source charge is still in this direction. So that means for the negative charge, you have the force and electric field opposite direction. That is easy to understand by using electric field equal force divided by charge. When charge is negative, electric field direction will be opposite direction from the force. Okay, so keep those in mind. So now this is again explained in that directional information. So if I have Q naught is positive, if Q is positive, Q is the source charge. Okay, so now your point of interest is P, that you have Q naught, right? So now if your Q naught is a positive number, we'll say this is positive, then it will create the electric force. They're going to repel each other, right? That is the force direction. And electric field also in the same direction. Why? Because this positive charge will create the electric field around that charge particle. Now my point of interest will be P. That place, I feel it is going outward direction. That's the electric field is. Right? Force and the field will be the same direction for the positive charge. But if it is a negative particle, what will happen is now I have a negative charge in here. So now this will say this is positive and your source charge is negative now. Now negative charge will create negative and positive charges as the attraction. Now attraction is this, but your electric field in this case will be also same direction because negative charge is the source charge has the electric field inward direction. So now what I feel in my point of interest, I am going to attract towards the negative charge as a field. That means electric field and force will be the same if you have a test charge as positive. Doesn't matter, you do it for source is negative or positive, your test charge is positive, that will has the electric field and the force same direction. Okay. Okay, so now we are ready to get more information about electric field. So negative charge always has, this is source charge, those are the things that you need to understand, that this is test charge, you even don't want the test charge. Test charge is that your point of interest that you need to think. You don't have the charge in there. That is your imagination that you're going to think there is a test charge, right? And but important thing is the source charge. So source charge will create the electric field. If it is negative, electric field on the source charge will be pointing towards that source charge. So that is the direction of the electric field. Okay, negative. Okay, so now if I bring a negative charge close to that, then you have electric field going outward direction. And also, if you bring the negative charge, you're going to get the electric field inward direction. That means this will say this is a negative charge. I bring the test charge as negative. Now electric field point in this way, but my electric force for the negative charge will be pointing outward direction. But if your test charge is positive, what will happen is then you still have electric field this way and also electric force in this way. That's the difference between negative and positive charges. But electric field direction coming from the source charge only. So that is you need to make sure you understand. And also electric field will be always perpendicular to the surface, and it is like your lines are more denser when the electric field is strong. Closer to the charge, they are denser. That means I have electric field more closer to the charge, but it is getting weaker and weaker when we go to the away from the charge. That is explained in this equation. You know that. So charge Q over R squared, because R squared relation, 1 over R squared relation is there. Okay, so now we finalize two things. One thing we finalize is if there is a positive charge, that is where your electric field start, and they are pointing outward direction. Always from the positive charge, they are perpendicular to the surface of the charge. And if there is a negative charge, you have electric field lines pointing inward the negative charge, and also they are perpendicular to the surface. Positive charge will create electric field, negative charge will end the electric field. So now that's the electric field, how electric field behave in charges. So now if I have positive and positive, definitely my electric field lines will be these blue lines, because they have electric field, like they're going to repel each other. Okay. And so now how to calculate it, we already know. So calculation can be done by using this. Again, don't plug the negative charges into the equation, because it has the magnitude formula that we are calculating magnitude only. Directions coming from superposition principle, that will be vector addition that you learn in your physics 1 class. Okay. Okay, so now let's see, I have a problem. I'm not going to solve the problem, but I'm going to explain to get an understanding, if you have problem, how you're going to solve it. How you're going to use superposition principle if you have many charges. We're going to start with 2 charges first, but we're going to move into the 3 charges, 4 charges. If you want, you can add many charges, right? So now I have Q1, Q2, and Q3 located with the origin, and asking you to find the electric field produced at the origin. Now you need to understand your point of interest. This is point of interest. To calculate the electric field, I don't want a test charge. So electric field, you can calculate anywhere your point of interest is. That is where the origin in this case, right? That is one thing. And next thing is understanding your sources. Sources in this case, Q1, Q2, and Q3. So since the question is not complete, I'm going to take some example. We'll say this one is given some negative value, this one is given as positive charge, and this one is given as positive charge. Those things should be given. So now all the charges is staying on d distance, right? That means whatever electric field created at the center from each charge will be, the distance will be the same, but the electric field value will be different, because electric field depend on the charge also, right? So important thing is drawing free body diagram. So free body diagram is the basically pose diagram, in this case electric field or vector diagram that we're going to draw, right? In this case also you have 3 charges. So now if I have a source, if I have a point of interest here, what it do is, we'll say, we will start from this charge. This is source charge. This charge will create electric field outward. We know that, right? After you know that, you even don't want to draw it. What I want to draw it at the your point of interest place only. Electric field is this way in for this charge. I'm going to say E. I don't know why I start from the Q3, but it is EQ3. Right? And then you need to go to the other charges. I have one charge in here, Q1. So that is a negative charge. Negative charge will create electric field inward direction to the charge in everywhere. But what I care is at this point. So this point, I have electric field created in this direction, that will be EQ1, right? So there is one more left. So this one is a positive charge that will create an electric field outward. And then after you realize that, in that point, in this point, your electric field will be in this direction again, because it is outward direction EQ2, right? So now I have EQ1, EQ2, EQ3. You definitely will be able to calculate those things. EQ1 is equal Coulomb constant. Q1, just the magnitude. Don't write the negative numbers. Q1 divided by distance d to the power 2. And then EQ2 will be KQ2 divided by distance to the power 2. And EQ3 is KQ3 divided by distance to the power 2. So now these are different numbers. These are in different direction. Can I add these 3 together to find the electric field? No, that's why free body diagram is important. Now you need to write x component from each vector by defining your coordinate system. So that means you need to define your coordinate system first. Your coordinate system, in this case, it is origin given. This is your x direction. This is your y direction, right? So now you're going to do your analysis towards x direction, y direction, and find your net E toward x direction from all EQ1, EQ2, and EQ3, and find EY component from EQ1, EQ2, and EQ3. And after you find those two values, you're going to use the Pythagorean theorem that you're going to square this and take the square root, and that will give you the magnitude only. Then find the direction by using tangent of theta. Then you will be able to find the angle of your resultant vector. So that is the process that you need to follow. Review the vector component method that you learn in your physics 1 class many times, that you will be able to do the problem easily. Okay, so now physics 2, what you learn is calculating this electric field. Those are the things you learn in physics 2. Other everything is application of your vectors addition rules that you learn in physics 1 class. Okay. And electric flux. So electric flux is can be defined as number of electric field lines that pass through the material. If I have a material in here, if this is the electric field, how many electric field lines that I can pass through this surface area, we call it as the electric flux. Electric flux measured by using, this is the notation that we're going to use, and units will be Newton meter squared divided by Coulomb. Okay, but it is electric field times cross-sectional area times cosine of theta is the formula. So that means electric flux is depend on how strong your electric field is, depend on your cross-sectional area, depend on what angle you're going to hit the surface area. So it's not always parallel to the your plane. You can have some tilted angle, then you need to take the angle between cross-section and the surface area, cross-section and the electric field. So that case, your electric flux will be able to calculate. Now it's very important that when theta equals 0, you know that cosine 0 is 1, that will give you the maximum flux. That will be the condition that I have, the condition that I try to show you in earlier. So this condition, that means my electric field, see the field is this pen, and will be basically parallel to the my cross-sectional vector. Cross-sectional vector will be pointing towards that. That means cross-section of your screen will be pointing towards you, right? So cross-section of this part is pointing this direction. Because of that, my E and cross-section will be parallel to each other. That means that is the 0 degrees, that is the maximum electric flux, because this turn into 1 when 0 degrees. And when you have electric field something like this, that means they are 90 degrees each other. In that case, you have electric flux 0. That is the electric flux is. Okay. So now Gauss law, although we are not going to calculate by using Gauss law, I want you to get an understanding what Gauss law explaining to you. So Gauss law is saying that if you calculate the electric flux by choosing any closed surface, that electric flux will be able to calculate by using charge that enclose on that surface area divided by the epsilon naught. That is what the Gauss said. Now, by combining Gauss law into the electric flux that we learned earlier, we will be able to calculate the electric field in any case, any object. If it is an irregular shape, if it is a different shape, still we will be able to use the Gauss law for calculation. So Gauss law is saying enclosed area, if you calculate how many charges you have inside that area, divide by permittivity constant, give you the electric flux. Okay, that's the Gauss law. Simple example is if you have charge Q in here, your enclosed charge inside this is we call as Gauss surface, this orange line Gauss surface. Now enclosed charge is Q, Q going to divide by epsilon naught, then you're going to get the electric flux from that source. And if you have 2Q source, then you have electric flux in this case, 2Q divided by epsilon naught. And if you have negative 0.5Q, then definitely you have negative 0.5Q divided by epsilon naught flux that will create in electric field inward direction because it is a negative charge. Okay. Okay, so now we're going to move into the conductors and properties of conductors. We call it as in electrostatic equilibrium case. So when there is no net motion of the charges within the conductor, we call it as electrostatic equilibrium. So that means when you have a conductor at rest, that this conductor does not have a motion of charges, that is called it as electrostatic equilibrium. Why there is no charges? I would say there is charges, but no motion of the charges. That is the electrostatic equilibrium. So now, if you have a conductor in this situation, that means no motion of the charges, electric field, let's say this is my conductor, electric field inside is always zero. There is no electric field inside the conductor unless you connect into the sources that we're going to discuss later. But sitting conductor at electrostatic equilibrium, there is no electric field. And later on, next chapter, we're going to learn about conductor has no potential difference because E equals 0. Because of that, your potential throughout the conductor, change of potential is 0. That means potential is a constant on the conductor. Right. In addition to that, conductor can have the charges, but inside the conductor, there is no charges. If it is a sphere, your charges of the conductor will stay on the sphere, not inside. Those are the properties of electrostatic equilibrium, right? So Faraday cage is one example for the static equilibrium. That's why that if there is a lightning, that if you are inside the car, unless you have electric if you create the electrocutor, then you're going to have a kind of lightning. But other than that, if you are inside the car in the thunderstorm, it is a conductor that you are inside, you seems to be safer than staying outside. So that is the principle behind the Faraday cage that we can have some demonstration on the laboratory. You can see some demonstration on the laboratory as a demonstration, not as an experiment. Those informations will be about the conductor. And now electric field lines, we learn how it will work, right? Positive charge will create electric field lines, negative charge will end in electric field lines. So now if I have a conductor, what will happen is there is a circular conductor in here. If I have a positive plate and negative plate here, positive plate will create electric field lines, negative plate will create end the electric field lines. But when there is a conductor, what will happen is within the conductor, you don't have electric field line. That's why I don't have red line inside. But because of this positive, they induce this surface as negative and this surface as positive. Then there is electric field on the left and right, but no electric field inside. Okay, and this is another one. This is a cavity is the conductor. There is no electric field inside the cavity. Okay, and this is another example that you have a positive charge, and this is the conductor in this time. So inside the conductor, no red line. There is no electric field lines, but here I have electric field lines because positive charge will create it outward direction, and then this plate that I have will charge as negative. Now this plate will charge as positive. Because of that, you have electric field lines again going outward direction. That features come in because of the conductor will not have electric field lines. Okay. And so now electric field line behavior in the conductor and the metallic sphere. So now if I have a conductor, as I mentioned, If it is a conductor, there is no electric field lines inside. Because of that, if I plot it, your electric field lines will be 0 from this point to this point. But when it comes to the surface, then your electric field lines going to behave as your electric field, as we know. Then it will be 1 over r squared behavior. That's for the conductor. But if it is a metal that is not a conductor, but it is a metal that I have electric charges everywhere in the surface and also inside. If I have everywhere charges in the surface and the inside, then if you calculate electric field until radius, your electric field will be linear. So we are not going to calculate that for your class, but that will be easily calculated by using charge density. Okay, but after that, it will behave as we know the behavior of the electric field from the source charge when you go further away from the charge. This is the behavior of the electric field within the conductor and within the metal. Okay, so now draw electric field lines. You're going to draw this in your laboratory also, and it's very important concept. Electric field lines start from positive, ending with negative, always perpendicular to the surface. Those are the things we learn. Direction is important since it is a vector. So draw electric field lines for two charges with charge equal in magnitude separated by small distance d. So now this will be the behavior of the electric charge, positive, positive, they have electric field. It start from the positive, but since there is no negative charge, you don't know where it ends. So now second case, electric field lines, again two charge particle, equal magnitude but opposite sign. So that will be symmetrical. So you have starting from positive, ending with negative. So that will be the electric field lines. We call it as dipole system later on. And then draw electric field lines of two charge particles, but they are different magnitude. Now what will happen, since my 2q is greater in magnitude in charge, then your field lines are denser in 2q area. Because of that, you don't have symmetrical lines in there, but still work starting from positive, ending with negative, arrow direction same, but they are not symmetrical. And also your 2q is more charged. Because of that, electric field is more stronger closer to the 2q. And my last one is two plates that you're going to do it in your laboratory that will create the electric field lines starting from positive and ending at negative. They are almost perpendicular to the plates in the middle, but there is winding at the end that you will see, but there is no electric field lines here or there. Okay. Okay, so now we talk about the electric field lines. We talk about how it will be able to draw, and this is it again. The visualization of the questions, the problems that we have done. Okay, so now we're going to move into the dipole. So dipole is basically calling as positive and negative charges together. If you have equal positive and equal negative, then that system we call it as the dipole, but they are opposite charges. So when this can happen in common most molecules and antenna systems, we have this dipole system. So what basically doing, you know, that water molecule that you have two hydrogen and one oxygen, as you have it in here, this will create a dipole moment that we call it as the P in here. Right, so P letter. So dipole moment is basically will be able to calculate by using one of the charge times the A. If they have same charge, Q will be the same, and distance between these two charges. If this one is Q, distance between these two A, then if you multiply Q times A, you're going to get the dipole moment. Dipole moment. Okay, dipole moment is a vector that will always point from negative charge to positive charge, negative to positive charge direction a vector that created because of these charges. We call it as the dipole moment. That's a very important concept that we need it for magnetism, moment, and antenna system. So these are, we call it as the moment that will be very helpful to get more detail about the systems. Okay, so now, but in your class, we are not going to solve any of those problems, but only thing I want you to take a look. If you have a dipole system, if you calculate the electric field anywhere in this system, here, outside, here, it doesn't matter where your point of interest is, dipole moment and the electric field that you are calculating in your point of interest anywhere in this dipole system will be proportional to distance 1 over r cube. R is the distance from dipole system to your point of interest, right? So that is depend on r to the power cube. But earlier, you remember single charges, electric field is proportional to 1 over r squared. In this case, it is 1 over r cube. Okay, so that is for the dipole system. So I have calculated dipole system when you have when you have your point of interest at on the axis of the dipole and out of the dipole, it is still 1 over r cube relation. Okay. Okay, so now I want you to think, because we are working with point-like charges in your class, but real systems are not point-like system. We have a charge rod. This is can be a rod that is have the charges everywhere. Then I can have a surface area that have a plate of charges, and I can have the cubic shape of the area, volume charge, right? Charge can be stay on the line, area, or volume. In that case, to compute electric field by using Gauss law, you need to consider how charge is distributed on this area, volume, or the line. So that we need to consider the charge density in each cases, that we need calculus for that to calculate the rest of the calculations that we are not going to do. But understand that in real life scenario that we have charge line or area or the volume. Okay. Okay, so now my next step is motion of charge particle inside the electric field. So now I want you to understand something here. So this will be basically very important thing, that if you need to project the particle inside the electric field, that how you going to project the particle, right? Simple example, I have length L plate in here, negative charge in this side and positive charge in this side. Whenever I know that positive and negative electric field lines will be this one. So I have E upward direction for the system. So now I have a particle that I'm going to project to the electric field. We'll say my charge particle is negative charge Q, right? I'm going to project it. When I project this particle, as soon as it enters the electric field, we'll say here, negative charge. When it enter electric field, what will happen to this charge particle? Because I have electric field upward, definitely since it is negative, this particle has electric force downward direction, electric force downward direction, right? So now, since I have electric force downward direction and this object has the velocity, because of that, there is an acceleration that will create the force. That force will be pointing in this direction. Now I have a Newton's law force that created by because of the velocity, and I have electric force that created by because of electric field. Then this object will choose the resultant force in between these two and then decide to go in parabolic path and attract towards the positive terminal. Okay, so that happen if it is a negative charge. If it is a positive charge, what do you expect happen? So if it is a positive charge, then your electric field is still there. But if this is a positive charge, what will happen is when it come to here, you have electric field and electric force in this direction. And then there is a force this direction because of the velocity, then it will choose the path that you have it in this direction, and then your positive charge is going to attract to the negative terminal. So that's the way that charge will move inside the electric field. Okay, so now capacitors that we have two plates. So what is the electric field on the two plates, in between two plates? It's very easy to understand, because as I mentioned, this positive charge will create the electric field outward, everywhere, outward, outward, everywhere. This will create the electric field inward, 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 and inward, right? So now because of this electric field created by this plate, and also it will create the electric field by using this plate, because of that, outside electric field going to be zero, almost zero. Okay, so maybe little electric field there, but almost will be zero. But what will happen inside? Inside, this will create electric field this way. This also will create electric field this way. Then inside, I will add up these two electric field. Then your electric field will be stronger in between two plates. That electric field will be able to calculate. We can derive this equation by using Gauss law, but not needed in your class. Electric field on the capacitor, I mean inside two plates, will be charge distribution divided by the epsilon naught. Sigma is, we call it as the surface charge density. So that means charge per unit area, that will be the surface charge density, okay, on the surface. Okay, so now electrostatic applications. There are many applications on electrostatic, right? So we know that it will play a very important role in molecular biology. So molecules such as protein or nucleic acid or so on, those all are important to life, and they are usually electrically charged, right? So DNA itself, you know that it is highly charged because of that electrostatic forces and the electric field. This molecule tied together and keep this molecular structure and the strength because of the electrostatic forces and fields. And Van de Graaff generator, last session also I mentioned that you have a video in the demonstration. Van de Graaff generator is basically creating high voltage dome that we can get the electricity to the outside without even touching it. Simple example is I have a kind of connection to the power that we have. After you connect in there, there is a call it as the belt. There is a belt. That belt will carry the charges. You see that this belt will carry the charges, and then when it comes to this pulley side in here, there is a connection to this outer dome. That is a conductor. Then this charge is distributed to this conductor. Then when it will come as neutral, and next time it will collect the charges again and again, distribute into the outer dome. Now this dome is a high voltage dome that if you go and touch it, make sure that this is a demonstration that you can do. If you have a setup, you need to be make sure that you are in insulator on top of the insulating table. Otherwise, electricity will travel through your body to the ground. Then you're going to be electrolyte. So you're going to have a insulating table. If you go on top of the insulating table and if you touch the dome, those all here are going to charge as positive, and then you will see your messy hair with the this electrostatics, because it transfer charges into your body. Then your body is charged, right? So, and in addition to that, in this setup, you can even light up the neon light bulb if you've been closer to that, because you have potential difference here to here. Without connection, without wires, you will be able to light it up, those light bulbs, by using Van de Graaff generator. And most of the photocopy machines, laser printers, jetting printers, we have these applications using of electrostatic field field and the forces. And human body itself, a charged particle, we have electric signal everywhere in our body. Okay, those are the application of the electric force and electric field. So I'm going to stop this session here. Make sure that you do your worksheet problems together and also individually later on to understand how we're going to apply those things into physical applications. And make sure you do the homework also.